Hello there, and welcome to the Drowsy Inquirer. I'm so glad you're here tonight because we're about to follow the fastest traveler the universe has ever known. Tonight, we're exploring light. Wherever you are right now, take a moment to notice the light around you. Maybe it's the soft glow of a screen, the dim warmth of a bedside lamp, or the faint silver edge of moonlight slipping through a curtain. Whatever it is, that light has a story. Every photon reaching your eyes right now has been on a journey, sometimes a short one across a room, sometimes an ancient one across the cosmos. And each one carries information, energy, and a quiet kind of beauty that most of us never stop to consider. Light is the reason you can see anything at all. It is the reason plants grow, the reason the sky has color, and the reason you know what a distant star is made of without ever touching it. It bends around massive objects, slows down in glass, and travels so fast that nothing in the universe can overtake it. And yet, for all its speed, for all its power, light is also gentle. It lands on your skin without weight. It fills a room without sound. It crosses billions of years of emptiness and arrives as softly as a whisper. Tonight, we will follow light from the back of your own eye to the edge of the observable universe. We will watch it bend, split, slow down, and disappear. We will meet the creatures that make their own light, the scientists who first measured its speed, and the ancient civilizations that worshipped it. And somewhere along the way, we will realize that light is not just something we see. It is something we are made of. If this kind of quiet curiosity brings you comfort or helps you drift toward sleep, consider leaving a like or subscribing. It helps other restless minds find their way here too, one gentle night at a time. But for now, let your body settle, let your breath slow, and let's begin this long, unhurried journey through the most luminous substance in existence. You have never seen the present moment. This may feel like an odd place to start, but it is true. Right now, as light from your surroundings enters your eyes, it takes time to be processed. Photons strike the photoreceptor cells in your retina, triggering a cascade of chemical signals that travel along the optic nerve to the visual cortex at the back of your brain. That entire process, from the moment light touches your eye to the moment you become consciously aware of what you are seeing, takes roughly 100 to 200 milliseconds. It is a tiny delay. You will never notice it in everyday life, but it means that everything you see, everything you have ever seen, is not the world as it is right now. It is the world as it was a fraction of a second ago. Your brain takes that slightly outdated information and constructs a seamless, convincing picture that feels immediate. It fills in gaps, smooths over delays, and presents you with an experience so polished that you believe you are witnessing reality in real time. But you are not. You are always watching a replay. The light that carries your world to you is fast, extraordinarily fast. But even light needs a moment to arrive, and your brain needs a moment more to understand what it has received. In the most intimate sense, you live just behind the present, watching it through a window that is always, imperceptibly, a heartbeat late. You can only see a tiny fraction of the light that exists. The light your eyes can detect, the rainbow of colors from deep red to vivid violet, feels like everything. It feels complete. But visible light is only a vanishingly small sliver of a much larger spectrum. If you stretch the entire electromagnetic spectrum out like a ruler from here to the sun, the portion visible to your eyes would be thinner than a pencil line. Beyond violet, there is ultraviolet light, the kind that causes sunburns and makes white shirts glow under black lights. Beyond that, X-rays, which pass through skin but not bone. Beyond that, gamma rays, the most energetic form of light in existence, born in nuclear reactions and the violent hearts of dying stars. On the other side of the spectrum, beyond red, lies infrared light, the gentle warmth you feel radiating from a campfire. Beyond that, Microwaves, the same kind of light that heats your food and also carries the faintest glow of the Big Bang across the entire sky. And beyond even that, radio waves stretching across kilometers, carrying music and voices and the quiet signals of distant spacecraft. All of these are light. They are all electromagnetic radiation, differing only in wavelength and frequency. Your eyes evolved to detect just one narrow band, the band that our sun happens to emit most strongly, the band that passes most easily through water and atmosphere. It was enough for survival. But it means you walk through a world flooded with light you will never see, a universe shimmering with invisible radiance in every direction. Color does not exist outside your mind. The red of a sunset, the green of a forest, the deep blue of the ocean on a calm day, these feel like properties of the world. They feel like things that exist out there, painted onto surfaces and skies, waiting to be noticed. But they do not. Color is not a feature of the external world. It is an experience created entirely inside your brain. What exists out there are electromagnetic waves of different lengths. A wave with a length of about 700 nanometers strikes your eye, and your brain interprets it as red. A wave of about 530 nanometers becomes green. 450 nanometers becomes blue. But the waves themselves have no color. They are just oscillations in an electromagnetic field, as colorless as a radio wave or an X-ray. Your retina contains 3 types of cone cells, each sensitive to a different range of wavelengths, roughly corresponding to red, green, and blue. Your brain combines the signals from these 3 channels and constructs the full palette of colors you experience. This is why color blindness occurs. When one type of cone is absent or altered, the brain builds a different palette from the available information. Some animals see colors you cannot. Mantis shrimp have 16 types of photoreceptor cells. Many birds can see ultraviolet light, revealing patterns on flowers and feathers that are completely invisible to you. The world does not look the same to any 2 species, and because color is not in the world. It is in the eye and in the mind behind it. The sky is not truly blue. If you step outside on a clear day and look up, the sky appears to be a gentle, uniform blue. It feels as natural as breathing, but the sky has no color of its own. It is not painted. It is not made of blue material. The blue you see is a trick of physics, played out between sunlight and the molecules in Earth's atmosphere. Sunlight is white, meaning it contains all the colors of the visible spectrum blended together. When this white light enters the atmosphere, it collides with the tiny molecules of nitrogen and oxygen that make up the air. These molecules are much smaller than the wavelength of visible light, and they scatter shorter wavelengths, blue and violet, far more effectively than longer wavelengths like red and orange. When this phenomenon is called Rayleigh scattering, violet light is actually scattered even more than blue, so in theory, the sky should appear violet. But your eyes are more sensitive to blue than to violet, and some of the violet light is absorbed in the upper atmosphere. The result is that your brain perceives the scattered light as a soft, even blue. From the surface of the moon, where there is no atmosphere, the sky is completely black, even during the day when the sun is shining brightly. The blue sky is not a feature of the universe. It is a feature of Earth, a delicate interaction between starlight and air that happens to create one of the most soothing sights in nature. Every sunset is a light filtering experiment. As the sun sinks toward the horizon, the light reaching your eyes must pass through a much thicker layer of atmosphere than it does at noon. At midday, sunlight travels through a relatively thin column of air directly overhead, but near the horizon, it cuts a long, shallow path, sometimes passing through more than 30 times as much atmosphere. Along that extended path, the shorter wavelengths, blue and violet, are scattered away almost entirely. They bounce off in every direction before they can reach you. What remains is the longer wavelengths, the oranges, the reds, the deep amber tones that spread across the sky during those final minutes of daylight. Dust, moisture, and even volcanic aerosols in the atmosphere can enhance the effect, scattering additional wavelengths and creating vivid pinks, magentas, and fiery golds. This is why sunsets after large volcanic eruptions can be particularly spectacular, and why humid evenings often produce richer colors than dry ones. No two sunsets are exactly alike, because the atmosphere is never exactly the same twice. The mix of particles, the humidity, the altitude of clouds, the angle of the sun, all of these variables combine in a slightly different recipe each evening. Every sunset is a unique, unrepeatable experiment in the filtering of light, conducted silently across the sky, free for anyone who thinks to look. Your eyes can detect a single particle of light. In the 1940s, a series of experiments confirmed something remarkable about human vision. When fully adapted to darkness, which takes about 30 to 40 minutes as the pupils widen and the rod cells in the retina reach maximum sensitivity, the human eye can detect a single photon, one particle of light, the smallest possible unit of brightness. A photon is the quantum of the electromagnetic field. It is the tiniest package of light that can exist. It has no mass. It has no size in the traditional sense. And yet, when one of these vanishingly small entities strikes a rod cell in your retina, it can trigger a molecular change, sending a signal through the optic nerve to your brain. In laboratory conditions, subjects have reported seeing flashes when as few as 5 to 7 photons reach their retina, with perhaps only 1 or 2 actually being absorbed by individual rod cells. This means your eyes operate at very nearly the physical limit of what is possible. You cannot build a biological light detector much more sensitive than the one already sitting in your skull. Evolution spent hundreds of millions of years refining this instrument, and it arrived at something extraordinary, a sensor so delicate that a single quantum of light is enough to register. The next time you find yourself in deep darkness and notice the faintest glimmer, perhaps a distant star, perhaps the last trace of twilight, consider that you may be detecting individual photons, the smallest messengers in the universe, arriving one by one, and your eyes are catching them. Fireflies write love letters in light. On warm summer evenings in certain parts of the world, the air fills with small, drifting sparks of yellow-green light. Fireflies, or lightning bugs, produce this glow through a chemical reaction in their abdomens. An enzyme called luciferase acts on a molecule called luciferin in the presence of oxygen and a molecule called ATP, producing light with almost no heat. It is one of the most efficient light-producing reactions known, converting nearly all of its energy into visible light, far more efficient than any incandescent bulb. But the beauty of firefly light lies not just in how it is made, but in why. Each species of firefly has its own unique flashing pattern, a specific rhythm of blinks and pauses. Males fly through the air, broadcasting their pattern, and females perched in the grass respond with their own time flash if they recognize a match. The conversation is a courtship, a dialogue carried out entirely in pulses of cold light. Some species synchronize their flashes. In the Great Smoky Mountains of Tennessee, thousands of Photinus carolinus fireflies blink in perfect unison, creating waves of light that roll through the forest like a slow, silent heartbeat. Scientists believe this synchronization helps females distinguish their species from the visual noise of other firefly species flashing nearby. There is something quietly magical about a creature that speaks in light. No sound, no touch, just a glow in the dark, repeated with patience, hoping that somewhere in the night, the right eyes are watching. Light is both a wave and a particle, and neither fully. For centuries, scientists argued about the nature of light. Isaac Newton believed light was made of tiny particles, which he called corpuscles. Christian Huygens argued it was a wave, spreading outward like ripples on a pond. Both sides had evidence. Both sides had compelling arguments. And as it turned out, both sides were right and both were incomplete. In the early 19th century, Thomas Young's double-slit experiment seemed to settle the debate in favor of waves. When light was passed through two narrow slits, it created an interference pattern on a screen behind them. Bright and dark bands that could only be explained if light behaved as a wave. Particles would have simply formed two bright lines. But then, in 1905, Albert Einstein explained the photoelectric effect by proposing that light comes in discrete packets of energy, quanta, later called photons. This was particle behavior, and it could not be explained by waves alone. The resolution is one of the strangest truths in physics. Light is not a wave. Light is not a particle. It is something else entirely. We're something that does not have a perfect analogy in everyday experience. When you design an experiment to look for waves, light behaves as a wave. When you design an experiment to look for particles, light behaves as a particle. It is as if light answers whatever question you ask, but never reveals its full nature at once. This is called wave-particle duality, and it is not a limitation of our instruments. It is a fundamental feature of reality at the quantum level. Light simply is what it is, and what it is does not fit neatly into any single human category. A photon carries energy but has no mass at all. This is one of the most counterintuitive facts in physics. A photon, the fundamental particle of light, has exactly zero mass. It weighs nothing. It has no substance in the way that a grain of sand or a molecule of air does. And yet, it carries energy. It carries momentum. It can push things. It can heat things. It can break molecular bonds and trigger chemical reactions. The energy of a photon is determined by its frequency, described by the equation E equals h times f, where h is Planck's constant and f is the frequency of the light. A high-frequency photon, like a gamma ray, carries enormous energy. A low-frequency photon, like a radio wave, carries very little. But no matter its energy, its mass remains zero. This is possible because of Einstein's famous equation, E equals mc squared, but applied in a more general form. Energy and mass are related, but they are not identical. A photon demonstrates this beautifully. It is pure energy in motion, untethered from the weight that governs everything else in your daily experience. And because it has no mass, a photon must travel at the speed of light. It cannot slow down. It cannot stop. It cannot rest. From the moment it is created to the moment it is absorbed, a photon moves at exactly 299,792,458 meters per second. It knows no other speed. It exists only in motion, a tireless messenger, carrying energy across the universe without ever pausing to rest. Nothing in the universe can travel faster than light. This is not a suggestion. It is not a speed limit posted on a cosmic highway, waiting to be broken by better technology. The speed of light in a vacuum is a structural feature of space-time itself. It is woven into the fabric of the universe as deeply as the dimensions of space and the flow of time. Einstein's special theory of relativity explains why. As an object with mass accelerates, it gains energy. But as it approaches the speed of light, the energy required to accelerate it further increases without bound. To push a single gram of matter to the speed of light would require infinite energy. It is not just impractical, it is impossible. This speed limit has profound consequences. It means that information cannot travel faster than light. It means that cause and effect are preserved, because no signal can arrive before it is sent. And it means that the universe has a built-in delay, a fundamental lag between events that prevents the cosmos from being instantaneous. Light travels at about 300,000 kilometers per second. In 1 second, it could circle the Earth 7.5 times. In 1 year, it covers nearly 10 trillion kilometers. And yet, even at this staggering speed, light from the nearest star beyond the sun takes over 4 years to reach you. The universe is so vast that even its fastest messenger needs billions of years to cross it. Speed, in the end, is relative, but the speed of light is absolute. It is the one constant that every observer in every corner of the universe agrees upon, no matter how fast they are moving. It is the universe's one unbreakable rule. From light's own perspective, time does not exist. This is perhaps the most mind-bending consequence of Einstein's relativity. As you approach the speed of light, time slows down, clocks tick more slowly, biological processes stretch out, and at the speed of light itself, time stops entirely. A photon, traveling at the speed of light, does not experience the passage of time. From the photon's frame of reference, if we can even call it that, its creation and its absorption happen simultaneously. A photon born in a distant star and absorbed by your retina 13 billion years later has, from its own perspective, existed for exactly 0 seconds. The entire journey, crossing galaxies, weaving past planets, arriving at your eye, happens in a single timeless instant. This is not a metaphor. It is a direct consequence of the Lorentz transformations, the mathematical framework that describes how space and time change at different speeds. At the speed of light, the time dimension contracts to 0. There is no before, there is no after, there is only the single eternal moment of being. We cannot truly imagine what this experience is like, because our consciousness is built entirely on the passage of time. But we can sit with the idea. A photon from the edge of the observable universe, having crossed 13 billion light-years of space, arrives at your eye tonight and, in its own silent accounting, no time has passed at all. For light, the universe is not vast. It is immediate. Light slows down when it passes through matter. In the vacuum of space, light travels at its maximum speed, the universal constant that nothing can exceed. But when light enters a material, like glass, water, or diamond, it slows down. In water, light moves at about 75% of its vacuum speed. In glass, about 67%. In diamond, it drops to roughly 41%. But what is actually happening is more subtle than it appears. Individual photons always travel at the speed of light, even inside a material. What changes is the way they interact with the atoms of that material. When a photon enters glass, it is absorbed by an atom, which briefly enters an excited state before re-emitting a new photon in the same direction. This process of absorption and re-emission takes a tiny amount of time. Multiply that delay across billions of atoms, and the overall effect is that light appears to move more slowly through the material. It is like walking through a crowded room. You are still walking at your normal pace, but you keep stopping briefly to excuse yourself past each person. Your speed between people has not changed, but your overall progress across the room is slower. This slowing of light is what causes refraction, the bending of light at the boundary between two materials. It is what makes a straw appear bent in a glass of water. It is what allows lenses to focus light and what makes diamonds sparkle with such fire. And it all comes from the simple fact that light, for all its speed, must stop and start with every atom it meets. Some particles can outrun light, and when they do, the universe glows blue. This sounds impossible. Nothing can travel faster than light. But there is a subtle and beautiful exception. The speed limit applies to light in a vacuum. When light slows down inside a material like water, other particles can exceed that reduced speed. And when they do, something extraordinary happens. A charged particle moving through water faster than the local speed of light creates a shock wave of electromagnetic radiation, similar to the sonic boom created by a jet exceeding the speed of sound. This radiation is called Cherenkov radiation, one named after the Soviet physicist Pavel Cherenkov, who first observed it in 1934. The result is an eerie, intense blue glow. If you have ever seen photographs of nuclear reactor pools, you may have noticed the water glowing with a vivid, almost otherworldly blue light. That glow is Cherenkov radiation, produced by electrons and other particles moving through the water faster than the speed of light in that medium. The particles are not violating Einstein's speed limit. They are not exceeding the speed of light in a vacuum. They are simply moving faster than the locally reduced speed of light in water. But the visual effect is stunning, a ghostly blue luminescence that feels like something from science fiction, yet is entirely real, entirely understood, and quietly beautiful. Refraction splits white light into every color you can see. When a beam of white light enters a glass prism at an angle, something beautiful happens. The light bends, and as it does, it separates. What was a single beam of white becomes a spread of colors, red on one side, violet on the other, with orange, yellow, green, and blue arranged in between. A rainbow born from geometry and glass. This happens because different wavelengths of light travel at slightly different speeds through glass. Red light, with its longer wavelength, slows down a little less and bends a little less. Violet light, with its shorter wavelength, slows down a little more and bends a little more. The result is that white light, which is a blend of all visible wavelengths, is fanned out into its constituent colors. Isaac Newton demonstrated this famously in 1666, using a prism to split sunlight and a second prism to recombine the colors back into white. He proved that white light is not pure, it is a mixture, and the colors of the rainbow are not created by the prism. They are revealed by it. Rainbows in the sky work on the same principle. Sunlight enters a raindrop, slows down, refracts, reflects off the back of the drop, and refracts again as it exits. Each wavelength bends at a slightly different angle, spreading the colors across the sky. Every rainbow you see is a personal one, formed by a unique set of raindrops between you and the sun. No two people ever see exactly the same rainbow. Light can be made to vibrate in only one direction. Light is a transverse wave, meaning its electric and magnetic fields oscillate perpendicular to the direction it travels. Normally, these oscillations happen in every possible orientation, up and down, left and right, and every angle in between. This is unpolarized light, the kind that comes from the sun, from a light bulb, from a candle flame. But light can be filtered so that only waves vibrating in a single plane are allowed through. This is called polarization. A polarizing filter works by absorbing all the light waves except those oscillating in one specific direction. The result is light that vibrates in a single, clean plane. Polarized sunglasses use this principle to reduce glare. When light reflects off a flat surface like water or a road, it tends to become partially polarized in the horizontal direction. Polarized lenses are oriented to block horizontally polarized light, cutting the glare while allowing other light through. The world looks sharper, calmer, and less blinding. Some animals can detect polarized light directly. Many insects, including bees, use the polarization pattern of the sky as a compass for navigation. Cuttlefish can see polarization and may use it for communication, sending signals to each other that are invisible to predators who cannot detect the polarization. Light, it turns out, has a direction not just of travel, but of vibration. And that hidden geometry, invisible to the naked eye, shapes navigation, vision, and the way entire species experience the world. Photosynthesis is the quiet engine that turns light into life. Nearly every living thing on this planet depends, directly or indirectly, on a single molecular event. A photon of sunlight strikes a chlorophyll molecule inside a plant cell, and that tiny collision sets off a chain reaction that converts light energy into chemical energy. This is photosynthesis, and it is the foundation upon which almost all life on Earth is built. The process takes place inside chloroplasts, small structures within plant cells that contain stacks of membrane-bound compartments called thylakoids. When light hits the chlorophyll embedded in these membranes, it excites electrons, raising them to higher energy levels. These energized electrons are then passed along a chain of proteins, driving the synthesis of ATP and NADPH, two molecules that the cell uses as energy currency. Meanwhile, water molecules are split, releasing oxygen as a byproduct. That oxygen is the air you breathe. The food you eat, whether it is a salad or a steak, traces its energy back to photosynthesis. Even fossil fuels are the compressed remains of ancient organisms that once captured sunlight millions of years ago. The energy in your muscles right now, the warmth of your body, the electrical signals firing in your brain, all of it began as a photon from the sun. Photosynthesis is not just a biological process. It is a bridge between the star nearest to you and the life within you. Every breath you take is a quiet acknowledgement that light somewhere was caught and transformed. Plants are green because they reject green light. This is a small fact that, once you hear it, rearranges something in your mind. The lush green of forests and meadows, the color most associated with life and nature, exists because plants do not want it. Chlorophyll, the pigment responsible for photosynthesis, it absorbs light most efficiently in the red and blue portions of the spectrum. These are the wavelengths it uses. Green light, which falls in the middle of the visible spectrum, is largely reflected or transmitted. It bounces off the leaf and into your eyes, which is why the leaf appears green. In other words, the greenness of plants is not the color they choose. It is the color they discard. The light they use is invisible to you in the context of the leaf because it has been absorbed. What you see is the leftover, the rejected wavelength, the light that was not needed. There is a quiet irony here. The color we most associate with nature, with growth, with life itself, is actually the color life turns away. And yet that rejected light is what makes the living world visible to our eyes. Without it, forests would look dark, almost black, and absorbing every photon and reflecting nothing. The beauty of a green landscape is, in a sense, a beautiful waste. The portion of sunlight that life did not need, gifted to your eyes instead. Most of the ocean's creatures carry their own light. Beneath the sunlit surface of the ocean, there is a boundary. Below about 200 meters, sunlight fades. Below 1,000 meters, it vanishes entirely. The deep ocean is a world of permanent darkness, a realm that has never seen a sunrise, where the only light that exists is the light that living things create, and they create a great deal of it. Bioluminescence, the ability to produce light through chemical reactions within the body, is found in more than 90% of the creatures that live in the deep sea. Jellyfish pulse with soft blue and green glows. Anglerfish dangle luminous lures above their jaws. Tiny dinoflagellates flash when disturbed, creating waves of light that ripple through the water like underwater lightning. The chemistry is similar to that of fireflies. A light-emitting molecule, usually a form of luciferin, reacts with oxygen in the presence of an enzyme called luciferase, producing light with almost no heat. Different species have evolved different versions of this chemistry, producing glows in blue, green, red, and even violet. The purposes of bioluminescence are as varied as the creatures that use it. Some use it to attract prey, some use it to communicate with mates, some use it as camouflage, matching the faint downwelling light from above so that predators looking upward cannot see their silhouette. And some use it as a defense, by releasing clouds of glowing fluid to confuse attackers. In the deepest, darkest waters on Earth, life did not accept the darkness. It made its own light. Your body glows, but your eyes cannot see it. In 2009, a team of Japanese scientists published a study that confirms something extraordinary. The human body emits visible light, not infrared radiation, which is related to heat and is well known. Actual visible light. Photons in the wavelength range that your eyes are built to detect. The emission is called ultra-weak bioluminescence, and it is roughly 1,000 times less intense than what your eyes can perceive. Using extraordinarily sensitive cameras, cooled to minus 100 degrees Celsius to eliminate thermal noise, the researchers captured images showing that the human body glows, with the face, particularly around the mouth and cheeks, emitting the most light. The glow fluctuates throughout the day, peaking in the late afternoon and fading at night, following the body's metabolic rhythms. The light is thought to be a byproduct of chemical reactions involving free radicals and fluorescent molecules within the skin. It is not purposeful in the way bioluminescence is in a firefly or a deep-sea fish. It is simply a quiet side effect of being alive, of the thousands of chemical reactions happening in your cells every second. You are, in the most literal sense, a being of light, not brightly, not dramatically, but genuinely. Right now, as you lie still and listen, your skin is softly emitting photons into the air around you, a faint, invisible aura that no human eye can see, but that science has confirmed is there. You glow. You have always glowed, and you will glow until the chemistry of life within you falls still. Sunlight becomes part of your body. When ultraviolet B radiation from the sun reaches your exposed skin, it triggers a remarkable transformation. A molecule in your skin called 7-dehydrocholesterol, a form of cholesterol, absorbs the UVB photon and undergoes a chemical change, eventually converting into vitamin D3. This is not a minor process. Vitamin D plays a critical role in calcium absorption, bone health, immune function, and mood regulation. Humans are one of the few species that rely heavily on sunlight for vitamin D synthesis. This is partly why human skin color evolved along a gradient correlated with latitude. Populations near the equator, where sunlight is abundant, develop darker skin with more melanin, which protects against excessive UV exposure while still allowing enough through for vitamin D production. Populations at higher latitudes, where sunlight is weaker, evolved lighter skin to maximize UV absorption during the shorter, dimmer days of winter. In a very real sense, your body is designed to eat light, not in the way a plant does through photosynthesis, but through a quieter, slower pathway. A photon leaves the sun, crosses 150 million kilometers of space in about 8 minutes, enters the atmosphere, reaches your skin, and becomes a vitamin that strengthens your bones and lifts your mood. You are not separate from the light around you. You are nourished by it. And even now in the dark, the vitamin D circulating in your blood carries the memory of sunlight you absorbed days or weeks ago. Light does not just illuminate you, it becomes you. Light sets the clock inside your brain. Deep within your eyes, there is a special class of cells that have nothing to do with seeing. They do not help you recognize faces or read words or admire a sunset. They exist for one purpose only: to detect the presence or absence of light and relay that information to the master clock in your brain. These cells are called intrinsically photosensitive retinal ganglion cells, and they contain a light-sensitive pigment called melanopsin. Unlike the rods and cones that handle vision, these cells respond primarily to blue light with a wavelength around 480 nanometers. When they detect this light, they send signals to a tiny region of the brain called the suprachiasmatic nucleus, a cluster of about 20,000 neurons that acts as your body's central timekeeper. This is how your circadian rhythm stays synchronized with the world outside. Morning light entering your eyes tells the master clock that it is daytime. The clock then signals the rest of your body to suppress melatonin, the hormone that promotes sleep, and increase cortisol, which promotes alertness. In the evening, as light fades, the process reverses. Melatonin rises, body temperature drops. The brain begins its slow transition towards sleep. This is why exposure to bright screens before bed can disrupt your sleep. The blue light from phones and computers activates those melanopsin cells, telling your master clock it is still daytime, even when the world outside is dark. Your body's ancient system, tuned over millions of years to respond to sunlight, it cannot distinguish between the sun and a glowing rectangle held 6 inches from your face. Right now in the darkness, your clock is winding down. The absence of light is doing exactly what it should. It is telling your body that it is time to rest. When light disappears, mood can follow. In the high latitudes of the world, winter brings not just cold, but a profound reduction in daylight. In places like Scandinavia, northern Canada, and Alaska, the sun may rise for only a few hours a day, or in extreme cases, not at all. And for a significant number of people, this loss of light brings a change in mood that goes beyond simple preference. Seasonal affective disorder, sometimes called SAD, is a form of depression that follows a seasonal pattern, typically emerging in autumn and winter and lifting in spring. Its symptoms include persistent low mood, fatigue, increased sleep, difficulty concentrating, and a craving for carbohydrates. Estimates suggest that it affects around 5% of the adult population in northern countries, with milder forms affecting many more. The mechanism is tied to light's influence on brain chemistry. Reduced sunlight leads to lower serotonin activity, a neurotransmitter closely linked to feelings of well-being. At the same time, the extended darkness causes the brain to produce melatonin for longer periods, amplifying feelings of drowsiness and lethargy. The circadian clock drifts out of alignment, and the body struggles to distinguish between day and night. One of the most effective treatments is remarkably simple: light therapy. Sitting in front of a bright light box that simulates daylight for 20 to 30 minutes each morning can reset the circadian clock and restore serotonin balance. Light, it turns out, is not just something you see. It is something your brain needs. Plants reach for light even in total darkness. If you place a young seedling in a dark room with a single small window, something quiet and persistent will happen. Over the course of days, the plant will bend toward that window. Its stem will curve, its leaves will orient, and its entire body will lean in the direction of the only light source available. This is phototropism, and it has been observed and studied for more than a century. The mechanism involves a hormone called auxin. In the presence of uneven light, auxin accumulates on the shaded side of the stem. Higher concentrations of auxin cause cells on that side to elongate more than cells on the lit side. The result is an asymmetric growth pattern that causes the stem to curve toward the light. Charles Darwin was among the first to study this phenomenon experimentally. In the 1880s, he and his son Francis demonstrated that the light-sensing region of a grass seedling was at the very tip, not along the stem. If they covered the tip, the plant did not bend, even though the rest of the stem was exposed to light. The signal was detected at the top and transmitted downward. There is something deeply evocative about a plant in darkness, slowly, silently reaching toward a distant glow. It has no eyes, no brain, no awareness as we understand it, and yet it moves toward light with a patience and determination that can span days. It does not rush. It does not give up. It simply grows, one cell at a time, toward the brightness it cannot see but somehow knows is there. Fire was the first light that humanity captured. For almost all of history, the only light available after sunset was the light of the stars and the moon. Darkness was absolute. Nightfall meant the end of activity, the beginning of vulnerability, the surrender of vision. And then, somewhere between 1 and 1.5 million years ago, our ancestors did something that changed everything. They learned to control fire. The earliest evidence of controlled fire use comes from sites in southern Africa, with charred bones and ash deposits suggesting deliberate, repeated burning. By 400,000 years ago, fire was a regular part of human life at sites across Africa, Europe, and Asia. Fire gave our ancestors light in the darkness. For the first time, the night was no longer a wall. Caves could be illuminated. Predators could be kept at bay. Food could be cooked, making more nutrients available and contributing to the growth of larger, more energy-hungry brains. And perhaps most importantly, fire created a gathering place, a circle of warmth and light in the darkness where stories could be told, bonds could be formed, and culture could begin to take shape. Every artificial light you have ever used, from a candle to a chandelier to the screen in front of you, is a descendant of that first captured flame. The human relationship with light is not just practical. It is ancient, intimate, and deeply tied to who we are as a species. We are the animals that refuse to let the darkness win. Candles held the night for thousands of years. After fire was tamed, the next great leap in portable light came in the form of the candle. The earliest candles, made from tallow, the rendered fat of cattle or sheep, date back at least 5,000 years. The ancient Romans used tallow candles regularly, and similar technologies appeared independently in China, where candles were made from whale fat, and in India, where wax from boiled cinnamon was used. Beeswax candles, which burned more cleanly and with less odor, became prized in medieval Europe, but were expensive enough that only churches and wealthy households could afford them. For most of history, ordinary people relied on tallow, which smoked, smelled, and guttered, but provided the only light available after dark. A single candle produces roughly 12 to 13 lumens of light. By comparison, a standard modern light bulb produces about 800. To illuminate a room to modern standards, you would need roughly 60 candles. For centuries, reading after dark was a luxury. Sewing, writing, and any detailed work required daylight or significant investment in candles. And yet there is something about candlelight that modern lighting has never quite replaced. The warm, flickering glow, the soft shadows, the gentle dance of the flame. Candlelight does not fill a room so much as it inhabits it, creating a pool of warmth surrounded by soft darkness. It is no accident that candles remain symbols of intimacy, ceremony, and peace. They are the oldest artificial light we still choose to use, not because we need them, but because something in us still responds to that quiet living glow. Gas lamps transformed the night into something livable. In the early 19th century, a new technology began to reshape cities across Europe and America. Gas lighting, fueled by coal gas piped through underground networks, brought a steady, reliable glow to streets that had known only darkness, moonlight, or the feeble flicker of oil lamps. London became one of the first cities to adopt gas street lighting on a large scale. By the 1820s, major thoroughfares were lined with gas lamps, and the transformation was immediate. Streets that had been dangerous after dark became walkable. Shops could stay open later. Theaters and restaurants flourished. The concept of nightlife as a social phenomenon was born. The light itself was warmer and steadier than candlelight, although still dim by modern standards. A typical gas lamp produced about the equivalent of a few hundred lumens, enough to cast a warm glow across a sidewalk, but not enough to banish shadows entirely. The streets of gaslit cities existed in a kind of perpetual twilight, bright enough to navigate, dim enough to retain a sense of mystery. Gas lamps also required a new profession, the lamplighter, who walked the streets each evening with a long pole, igniting each lamp one by one, and returned each morning to extinguish them. It was a ritual that marked the boundary between day and night, a human hand drawing the line between light and darkness across an entire city. The light bulb was not the work of a single genius. The story most people know is simple. Thomas Edison invented the light bulb. But the real story is far richer. and far more collaborative. As early as 1802, Humphrey Davy demonstrated the first electric light by passing current through a thin strip of platinum, which glowed but burned out quickly. In the 1840s, Warren de la Rue used a coiled platinum filament in a vacuum tube, producing a longer-lasting light, but the cost of platinum made it impractical. In 1878, Joseph Swan in England demonstrated a working incandescent lamp using a carbonized paper filament, and he began installing them in homes before Edison did. What Edison contributed and what made him famous was not the concept but the execution. His team tested thousands of materials to find a filament that would glow brightly and last. They settled on carbonized bamboo, which could burn for over 1,200 hours. Equally important, Edison developed the entire system around the bulb: generators, wiring, switches, meters, and power stations. He did not just create a light, he created an infrastructure. The incandescent bulb, in all its forms, works on a simple principle. Electricity passes through a thin filament, heating it to a temperature so high that it emits visible light. It is beautifully simple and remarkably inefficient, converting only about 5% of its energy into light and the rest into heat. But for over a century, it was enough. It brought light to homes, factories, hospitals, and schools, and it changed the shape of human life forever. Electric light erased the ancient boundary between day and night. For all of human history until roughly 140 years ago, the rhythm of daily life was governed by the sun. You woke when it rose. You worked while it shone. You rested when it set. Darkness was not an inconvenience. It was a fundamental boundary, as solid and non-negotiable as a wall. Electric light dissolved that wall. Factories could run 24 hours a day. Cities could function around the clock. Work, entertainment, travel, and communication became untethered from the solar cycle. The modern world, with its night shifts, its late-night television, its all-hours connectivity, is built entirely on the assumption that light is always available. But this liberation came at a cost. Human biology did not evolve for constant light. The circadian system, refined over millions of years, expects a clear distinction between bright days and dark nights. When that distinction blurs, the consequences ripple through the body. Disrupted sleep, impaired immune function, an increased risk of metabolic disease, and shifts in mood and cognition have all been linked to excessive artificial light at night. There is a quiet paradox here. We invented light to extend our day, and in doing so, we compromised our night. The very tool that freed us from darkness now intrudes upon the darkness we need. And somewhere in that tension, in the glow of a screen at midnight or the buzz of a street lamp outside a bedroom window, lies one of the subtle costs of being the species that learned to keep the lights on. The stars are disappearing behind a veil of light. On a truly dark night, far from any city, the sky is overwhelming. Thousands of stars are visible to the naked eye. The Milky Way stretches across the dome of the sky like a river of spilled milk, dense with light. Planets glow steadily among the flickering stars. And the sheer depth of the sky, the sense that you are looking into a volume rather than at a surface, can take your breath away. But most people alive today have never seen the sky. Light pollution, the cumulative glow of streetlights, signs, buildings, and vehicles, scatters off the atmosphere and creates a luminous haze that washes out all but the brightest stars. A study published in 2016 estimated that more than 80% of the world's population lives under light-polluted skies, and more than a third of humanity cannot see the Milky Way at all. The effects extend far beyond astronomy. Migratory birds, which navigate by starlight, become disoriented by brightly lit buildings, sometimes circling them until they collapse from exhaustion. Sea turtle hatchlings, which instinctively crawl toward the brightest horizon, in which should be the moonlit ocean, are lured inland by artificial lights and die. Insects swarm around lamps by the billions, disrupting pollination and food webs. Light pollution is not dramatic. It does not burn or explode or make headlines. It simply accumulates night after night until the sky that every human civilization before ours took for granted quietly vanishes behind a curtain of our own making. Some places still protect the darkness. In response to the growing loss of the night sky, a movement has emerged to preserve the world's remaining dark places. The International Dark Sky Association designates certain regions as dark sky reserves or dark sky parks, areas where artificial lighting is carefully managed to protect the natural darkness. Places like Namibrand in Namibia, Aoraki Mackenzie in New Zealand, and the Brecon Beacons in Wales have earned this designation. In these protected areas, lighting ordinances require that outdoor lights be shielded, dimmed, or turned off after certain hours. The result is a sky that looks much as it did centuries ago, dense with stars, luminous with the Milky Way, and achingly beautiful. Visitors to these reserves often describe the experience as transformative. People who have lived their entire lives under light-polluted skies see the Milky Way for the first time and are moved to tears. The sky, which they had always thought of as a flat, dark ceiling, dotted with a few bright points, reveals itself as a vast, deep, three-dimensional ocean of light. There is something worth protecting here, not just for science, not just for ecology, but for the ancient human experience of looking up and feeling small and connected and at peace. The dark sky is not empty. It is full, and it has been waiting quietly for you to see it. The speed of light was first measured using the moons of Jupiter. For most of human history, people assume that light traveled instantaneously. When you light a candle, the room brightens immediately. When lightning flashes, you see it at once. There seemed to be no delay, no travel time, nothing to measure. But in 1676, a Danish astronomer named Ole Rømer noticed something odd about the moons of Jupiter. He was carefully timing the eclipses of Io, Jupiter's innermost large moon, as it passed behind the planet. He expected the eclipses to occur at perfectly regular intervals. Instead, they were sometimes early and sometimes late, depending on where Earth was in its orbit relative to Jupiter. Rømer realized that the discrepancies could be explained if light had a finite speed. When Earth was closer to Jupiter, the light from Io's eclipse had a shorter distance to travel and arrived earlier. When Earth was farther away, the light took longer and the eclipse appeared late. From the size of the discrepancies in the known dimensions of Earth's orbit, Rømer estimated that light took about 22 minutes to cross the diameter of Earth's orbit. His estimate was roughly 30% too high, but the insight was revolutionary. Light was not instantaneous. It traveled at a finite, measurable speed. For the first time, humanity understood that even the fastest thing in the universe needs time to get from one place to another. And that understanding began with a man patiently watching a tiny moon vanish behind a distant planet. The sun you see is already 8 minutes old. Right now, the sun appears to hang in the sky, immediate and present, but the light reaching your eyes at this moment left the sun's surface about 8 minutes and 20 seconds ago. In that time, it crossed roughly 150 million kilometers of empty space at 300,000 kilometers per second. This means that if the sun were to suddenly vanish, you would not know for over 8 minutes. The sky would remain bright. The gravitational pull would continue. Everything would seem normal. And then, 8 minutes and 20 seconds later, the light would stop arriving, and the sky would go dark. A few minutes after that, the gravitational change would reach Earth, and the planet would drift off its orbit into the cold of interstellar space. This delay is not unique to the sun. Everything you see in the universe is a message from the past. The light from your ceiling lamp left it about a nanosecond ago. The light from the moon left its surface 1.3 seconds ago. Every sight you experience is old news, a recording rather than a broadcast. But with the sun, the delay is long enough to feel meaningful. The warm light on your face on a summer afternoon is not the sun as it is. It is the sun as it was, a portrait painted 8 minutes ago and delivered to you at the fastest speed the universe allows. You are always looking at a memory of the sun, and you have never, not once in your life, seen it in real time. We still bounce light off the moon to measure its distance. On the surface of the moon, at several locations visited by Apollo astronauts between 1969 and 1972, there are small panels covered with special glass prisms called retroreflectors. These are not powered. They have no electronics. They are simply arrays of corner cube prisms designed to reflect any incoming beam of light directly back toward its source. From observatories on Earth, scientists fire a pulse of laser light at one of these panels. The laser beam travels to the moon at the speed of light, hits the retroreflector, and bounces straight back. By measuring the time it takes for the round trip, scientists can calculate the distance to the moon with astonishing precision to within a few millimeters. The round-trip travel time is about 2.5 seconds. The moon is roughly 384,000 kilometers away, and it is moving. Thanks to decades of laser ranging, we know that the moon is receding from the Earth at a rate of about 3.8 centimeters per year, roughly the speed at which your fingernails grow. There is something wonderfully human about this. We walked on the moon, left a small mirror on its surface, and now, decades later, we shine a light at it and wait 2.5 seconds for the reflection to return. It is a conversation carried out in photons, a call and response between a planet and its companion, repeated night after night with patience and precision. Talking to Mars means waiting. When NASA engineers send a command to a rover on Mars, they cannot see the result in real time. The signal, traveling at the speed of light, takes between 4 and 24 minutes to reach Mars, depending on the relative positions of the two planets in their orbits. And then the response, also traveling at light speed, takes the same amount of time to come back. A simple instruction like drive forward 2 meters might take over 40 minutes for a round-trip confirmation. This means that Mars rovers cannot be driven like remote-controlled cars. They must be given a set of instructions each morning and left to execute them autonomously, navigating obstacles on their own, making decisions without real-time human input. Curiosity and Perseverance, the rovers currently operating on Mars, are equipped with hazard avoidance cameras and onboard computers that allow them to stop if they encounter unexpected terrain. But the fundamental constraint remains. When the conversation between Earth and Mars is always a delayed one, a monologue sent into the void with a hope that the reply, when it finally arrives, will bring good news. If humans ever travel to Mars, they will experience this delay personally. A phone call to Earth would have a gap of up to 48 minutes between speaking and hearing a response. Real-time conversation would be impossible. Messages would be sent and received like letters, crossing the void in packets of light, patient and unhurried. Voyager's whisper takes almost a full day to reach us. Launched in 1977, Voyager 1 is the most distant human-made object in existence. As of now, it is more than 24 billion kilometers from Earth, traveling outward through interstellar space at about 17 kilometers per second. It has crossed the heliopause, in the boundary where the sun's influence gives way to the interstellar medium, and it continues to drift further every day. Voyager 1 carries a small radio transmitter powered by a plutonium-based thermoelectric generator. The transmitter produces about 23 watts of power, roughly the same as a refrigerator light bulb. And yet the Deep Space Network, a system of enormous radio antennas spread across California, Spain, and Australia, can still detect its faint signal. That signal, traveling at the speed of light, takes more than 22 hours to reach Earth. When mission controllers send a command to Voyager, they must wait nearly 2 full days for a response. The conversation is among the slowest in human history, and the signal itself, by the time it arrives, is unimaginably faint. The power received by the antenna is measured in fractions of a billionth of a watt. It is less than the energy of a snowflake landing on the ground, and yet it carries data, real information, about the conditions at the edge of the solar system, transmitted by a machine that left Earth when most of the people alive today had not yet been born. Voyager will continue drifting outward, its signal growing fainter, until sometime in the mid-2030s when its power source can no longer sustain the transmitter. After that, it will travel in silence, carrying a golden record engraved with sounds and images of Earth, a message in a bottle cast into an ocean of light and darkness. A light year is a ruler, not a clock. The term light year sounds like a measure of time. It has the word year right in it. But a light year is actually a measure of distance, the distance that light travels in 1 year. And that distance is enormous. In 1 second, light covers about 300,000 kilometers. In 1 minute, 18 million. In 1 hour, over 1 billion. And in 1 year, light travels approximately 9.46 trillion kilometers. That is a 9 followed by 12 zeros. This distance, 1 light year, is the yardstick that astronomers use to measure the spaces between stars. The nearest star system to our Sun, Alpha Centauri, is about 4.37 light years away. That means the light arriving from Alpha Centauri tonight left its surface more than 4 years ago. You are seeing it as it was during a different season, a different year, a different chapter of your life. The brightest star in the night sky, Sirius, is about 8.6 light years away. The star Vega, one of the brightest in the northern hemisphere, is about 25 light years away. The center of our own galaxy, the Milky Way, is roughly 26,000 light years from here. These numbers are not just measures of space, they are measures of time embedded in space. Every distance in light years is also a look backward in time. The further you look, the deeper into the past you see. The universe does not separate space from time. It weaves them together, and light is the thread. There is a horizon beyond which no light will ever reach us. The observable universe is not the entire universe. It is only the portion from which light has had time to reach us since the Big Bang, 13.8 billion years ago. Beyond that boundary, there may be galaxies, stars and worlds without number, but their light has not yet arrived, and for some of them, it never will. The observable universe has a radius of about 46.5 billion light years. This number is larger than 13.8 billion because space itself has been expanding throughout the entire history of the universe. Light that left a distant galaxy 13 billion years ago has been traveling through space that has been stretching the whole time. So the galaxy is now much farther away than 13 billion light years. This expansion creates a horizon, a limit beyond which we can never see, no matter how long we wait or how powerful our telescopes become. Galaxies beyond the cosmic horizon are moving away from us faster than the speed of light, not because they are traveling through space at that speed, but because the space between us is expanding that fast. This means our observable universe is shrinking in a certain sense. Galaxies that are currently visible will, over billions of years, cross beyond the horizon and fade from view. Their light will be stretched to infinite wavelengths and vanish. From the perspective of the very far future, the sky will contain fewer and fewer visible objects, until eventually observers in our galaxy will look out and see nothing but darkness in every direction, with no evidence that other galaxies ever existed. The universe is expanding, and light carries the proof. In 1929, the astronomer Edwin Hubble made one of the most important discoveries in the history of science. By studying the light from distant galaxies, he noticed that nearly all of them showed a peculiar shift in their spectra. The spectral lines, the fingerprints of specific elements, were shifted toward the red end of the spectrum. And the further away a galaxy was, the greater the shift. This red shift, as it came to be called, is the result of the expansion of space. As the universe expands, the wavelength of light traveling through it is stretched. Longer wavelengths correspond to redder colors, so light from distant, receding galaxies appears redder than it would if the universe were static. The relationship Hubble discovered, now called Hubble's law, states that the farther away a galaxy is, the faster it is receding from us. This does not mean we are at the center of the expansion. Every point in the universe sees every other point moving away, like dots on the surface of a balloon being inflated. There is no center. There is only expansion, everywhere, all at once. This discovery transformed our understanding of the cosmos. The universe was not eternal and unchanging, as many had assumed. It was dynamic, evolving, and had a beginning. The red shift of distant galaxies was the first direct evidence that the universe began in a hot, dense state and has been expanding ever since, an event we now call the Big Bang. Light brought us this knowledge, not through brightness or beauty, but through a subtle shift in color, a quiet reddening that revealed the universe is not standing still. The darkness of the night sky is itself a profound mystery. This seems like the simplest observation in the world. At night, the sky is dark. But in the 18th century, a series of thinkers, most famously the German astronomer Heinrich Wilhelm Olbers, pointed out that this simple fact is deeply puzzling. If the universe were infinite, eternal, and uniformly filled with stars, then every line of sight in every direction should eventually end at the surface of a star. The entire sky should be blazing with light, as bright as the surface of the sun. There should be no dark patches, no gaps, no night at all. This is known as Olbers's paradox, and for centuries it had no satisfying answer. Some suggested that dust between the stars absorbed the light, but dust would eventually heat up and re-radiate the energy, producing the same brightness. Others proposed that the universe was simply not infinite, but this raised its own problems. The modern resolution combines two insights. First, the universe is not infinitely old. It is 13.8 billion years old, which means light from very distant stars has not had time to reach us yet. There are stars out there whose light is still on its way. Second, the expansion of the universe stretches the light from the most distant objects to wavelengths beyond the visible range, effectively dimming them out of sight. The darkness of the night sky, far from being ordinary, is evidence of the finite age and the expansion of the universe. Every time you look up at a dark sky, you are seeing proof that the cosmos had a beginning and is still growing. Darkness, it turns out, is not the absence of information, it is full of it. Gravity can bend light around corners. One of the most dramatic predictions of Einstein's general theory of relativity is that massive objects bend the path of light. Not because light has mass, but because massive objects curve the fabric of space-time, and light follows those curves. This effect, what's called gravitational lensing, was first confirmed in 1919 during a total solar eclipse. Arthur Eddington led an expedition to the island of Principe off the west coast of Africa, where he photographed stars near the edge of the sun during the eclipse. The positions of those stars were slightly shifted compared to their normal positions, exactly as Einstein had predicted. The sun's mass was bending the starlight passing near it, nudging the apparent positions of the stars. Since then, gravitational lensing has become one of the most powerful tools in astronomy. Entire galaxy clusters can act as cosmic magnifying glasses, bending and amplifying the light from far more distant objects behind them. In some cases, a single distant galaxy appears as multiple images, smeared into arcs or rings of light by the gravitational field of the foreground cluster. One of the most famous examples is the Einstein cross, where a distant quasar appears as four distinct images arranged around a foreground galaxy. The galaxy's gravity splits the quasar's light into four separate paths, each arriving at Earth from a slightly different direction. Light, which always travels in a straight line through flat space, follows curved paths through curved space. And because mass curves space, light bends around galaxies the way water bends around a stone in a stream. The universe is not just a container for light, it shapes light's journey, gently, invisibly, and with extraordinary precision. A photon born in the heart of the sun takes 100,000 years to reach the surface. When this fact is one of the most surprising in solar physics. The sun produces its energy through nuclear fusion in its core, where temperatures reach about 15 million degrees Celsius. In this inferno, hydrogen nuclei fuse into helium, releasing photons of gamma radiation. These photons are extraordinarily energetic, born in the densest, hottest place in the solar system. But they do not streak outward in a straight line. The sun's interior is so dense that a photon can barely travel a fraction of a centimeter before it collides with a particle, is absorbed, and is re-emitted in a random direction. This process, called a random walk, means the photon zigzags through the solar interior in a drunkard's path, taking an incredibly long time to work its way outward. Estimates vary, but the average time for a photon to travel from the sun's core to its surface is between 100,000 and 200,000 years. During that journey, the photon is absorbed and re-emitted so many times that it is no longer the same photon in any meaningful sense. Its energy is degraded, its wavelength lengthened. By the time it reaches the surface, what started as a gamma ray has become visible light and infrared radiation. And then, once it escapes the surface, it crosses the 150 million kilometers to Earth in just 8 minutes. 100,000 years of struggle inside the sun, followed by an 8-minute sprint through empty space. The sunlight warming your face has been trying to reach you for longer than human civilization has existed. Neutron stars spin like cosmic lighthouses. When a massive star exhausts its fuel and collapses, it can leave behind an extraordinarily dense remnant called a neutron star. These objects pack more mass than the sun into a sphere roughly 20 kilometers across. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. Some neutron stars emit beams of electromagnetic radiation from their magnetic poles. As the star spins, these beams sweep across space like the beam of a lighthouse. If one of those beams happens to point toward Earth during part of the star's rotation, we detect it as a regular pulse of light, and we call the object a pulsar. Pulsars are among the most precise clocks in the universe. Some spin hundreds of times per second with a regularity that rivals atomic clocks. The fastest known pulsar, PSRJ 1748-2446 AD, where rotates 716 times every second. Its surface at the equator moves at roughly 24% the speed of light. The discovery of pulsars in 1967 by Jocelyn Bell Burnell was initially so puzzling that the first signal was half-jokingly labeled LGM1 for Little Green Men, because the pulses were so regular they seemed artificial. They were not, of course. They were the spinning remnants of dead stars, sweeping beams of radiation across the cosmos like celestial lighthouses, patiently marking time in the darkness. The brightest flashes in the universe last only seconds. Gamma-ray bursts are the most energetic events in the known universe. In a span of just a few seconds to a few minutes, a single gamma-ray burst can release more energy than the sun will produce in its entire 10 billion-year lifetime. But they are brief, violent, and so luminous that they can be detected from billions of light years away. There are two main types. Short gamma-ray bursts, lasting less than about 2 seconds, are thought to result from the merger of two neutron stars or a neutron star and a black hole. Long gamma-ray bursts, lasting from several seconds to several minutes, are believed to occur when a very massive star collapses directly into a black hole, producing jets of material that punch outward through the star's outer layers at nearly the speed of light. In August 2017, astronomers detected both gravitational waves and a short gamma-ray burst from the same event, a neutron-star merger about 130 million light-years away. It was the first time a cosmic event had been observed in both gravitational waves and electromagnetic radiation simultaneously, opening a new chapter in multi-messenger astronomy. Despite their extraordinary power, gamma-ray bursts are not a threat to Earth from their current known sources. The nearest observed bursts have all been comfortably far away, but their existence reminds us that the universe is not always gentle. Amid the quiet drift of galaxies and the patient glow of stars, there are moments of unimaginable brilliance, flashes so intense that for an instant, a single point in space outshines everything else in the observable universe. The first light of the universe is still arriving. About 380,000 years after the Big Bang, the universe cooled enough for a profound change to occur. Until that moment, the cosmos was a seething fog of charged particles, so dense and hot that photons could not travel more than a short distance before colliding with an electron and scattering off in a random direction. Light was trapped. The universe was opaque. But as temperatures dropped below about 3,000 degrees Celsius, protons and electrons combined to form neutral hydrogen atoms for the first time. Suddenly, the photons had nothing to scatter off. They were free. In a single epoch, the universe went from opaque to transparent, and light flooded outward in every direction. That light has been traveling ever since. In over 13.8 billion years, the expansion of the universe has stretched its wavelength from visible light to microwaves. It is now known as the cosmic microwave background radiation, and it fills every cubic centimeter of space. It comes from every direction equally, with a temperature of about 2.7 degrees above absolute zero. When you tune a television to a channel with no signal and see static, roughly 1% of that static is caused by photons from the cosmic microwave background. You are seeing, in a very faint way, the afterglow of the birth of the universe. This light is not a relic in a museum. It is alive. It is arriving right now, passing through the walls around you, through the air you breathe, through your body. It has been traveling since before the Earth existed, before the sun ignited, and before the Milky Way took its spiral shape, and it will continue arriving for billions of years to come, growing ever colder, ever fainter, but never quite disappearing. Before that light was released, the universe was blind. For the first 380,000 years of its existence, the universe had no light in the way we understand it. Photons existed in unimaginable abundance, but they could not travel freely. Every photon was trapped in a dense plasma, colliding with charged particles almost instantly after being emitted, bouncing endlessly in a fog so thick that no image, no signal, no information could pass through it. If you could somehow stand inside that early universe, you would see nothing. Not darkness exactly, but a formless, blazing white in every direction, an incandescent haze with no depth, no distance, no detail. Everything would look the same, everywhere, a wall of light with nothing behind it. This is why the cosmic microwave background is sometimes called the surface of last scattering. It is the earliest moment from which light can reach us. Everything before it is hidden, not by distance, but by the opacity of the universe itself. We can study that earlier era through other means, through the abundances of light elements like hydrogen and helium forged in the first few minutes, through gravitational waves that may have left subtle imprints. But we cannot see it. Light was there, but it could not escape. The release of the cosmic microwave background was the moment the universe opened its eyes. For the first time, photons could travel in straight lines, carrying information across space. The universe became visible to itself. And that visibility, that transparency, is the foundation of everything we have ever seen. The reddening of distant light revealed that the universe is growing. When astronomers study the light from distant galaxies, they do not just measure its brightness, they study its spectrum, the specific wavelengths emitted by the elements within those galaxies. Hydrogen, helium, oxygen, and other elements each produce a unique pattern of spectral lines, like a fingerprint made of light. In the 1920s, astronomers began noticing that the spectral lines from distant galaxies were shifted toward the red end of the spectrum. This red shift meant that the wavelengths had been stretched, and the most natural explanation was that the galaxies were moving away from us. The further away a galaxy was, the greater the red shift, and therefore the faster it was receding. But the galaxies are not moving through space like ships sailing away from a port. Space itself is expanding, stretching the light as it travels through it. Imagine drawing two dots on a rubber band and then pulling the band from both ends. The dots move apart, not because they are sliding along the surface, but because the surface itself is growing. Light traveling across expanding space is stretched in the same way, its wavelength lengthening, its color reddening. This discovery, refined and confirmed by decades of observation, tells us that the universe was once much smaller, much denser, and much hotter than it is today. Traced backward in time, the expansion implies a beginning, a moment when all of space, all of energy, all of matter was compressed into an unimaginably dense state. The redshift of distant starlight did not just reveal that galaxies are moving apart. It revealed that the universe has a history, a story with a beginning, and that light has been carrying the evidence of that story across billions of years, waiting for someone to read it. The night sky answers one of the oldest questions in cosmology. Why is it dark at night? It seems like the simplest possible observation. The sun sets, the sky goes dark, stars appear. But behind this simplicity lies a question that puzzled some of the greatest minds in science for centuries. If the universe is infinite, eternal, and filled with stars in every direction, then every line of sight should eventually end at the surface of a star. The sky should be ablaze with light, as bright and uniform as the surface of the sun, where there should be no dark gaps between the stars. Night should not exist. This puzzle, known as Olber's paradox, resisted satisfying answers for over 200 years. Some propose that interstellar dust absorbs the missing light, but dust would eventually absorb enough energy to glow as brightly as the stars themselves. Others suggested the universe might not be infinite, but that raised equally difficult questions. The modern answer is elegant and profound. The universe is not infinitely old. It had a beginning, about 13.8 billion years ago. This means that light from the most distant stars has not yet had time to reach us. There are vast regions of the universe whose light is still on its way, and some whose light will never arrive because the expansion of space is carrying them beyond our horizon faster than their light can close the gap. Every dark patch in the night sky is not an absence. It is a message. It tells you that the universe had a beginning, that it is expanding, and that light, for all its speed, has limits. Darkness in this context is not emptiness. It is evidence. Light bends around massive objects, revealing hidden worlds. When light from a distant galaxy passes near a massive foreground object, like a galaxy cluster, it does not travel in a straight line. The mass of the foreground cluster warps space-time, and the light follows the curvature, bending around the obstacle like water flowing around a stone. This effect, predicted by Einstein and first confirmed in 1919, has become one of the most powerful tools in modern astronomy. Gravitational lensing, as it is called, can magnify distant objects that would otherwise be too faint to see. It can also distort their shapes, stretching them into arcs, rings, or multiple images, depending on the geometry of the alignment. In the most dramatic cases, called strong lensing, a perfectly aligned background source appears as a luminous ring around the foreground mass, known as an Einstein ring. In less perfect alignments, the source is split into multiple images, each arriving at Earth along a slightly different curved path through space-time. There is something quietly beautiful about gravitational lensing. The universe, through the sheer presence of mass, creates its own magnifying glasses. It bends light around obstacles, while revealing objects that would otherwise remain forever hidden. The cosmos is not just transparent to light. It actively guides it, sculpts it, and uses it to show us things we could never have seen on our own. A photon struggles for millennia inside the sun before finally escaping. The heart of the sun is a furnace of almost incomprehensible intensity. At its core, where temperatures reach 15 million degrees and pressures crush hydrogen nuclei together, nuclear fusion produces a torrent of energy in the form of gamma-ray photons. These photons are born with extraordinary energy, vibrating at frequencies far beyond anything your eyes could detect. But their journey outward is agonizingly slow. The sun's interior is so dense, so packed with ions and electrons, in that each photon travels only a tiny distance before being absorbed by a particle and then re-emitted in a random direction. This random walk, this endless sequence of absorption and re-emission, means that a photon born in the core may take anywhere from 100,000 to 200,000 years to reach the surface. Along the way, the photon's energy is gradually diluted. Each interaction transfers some energy to the surrounding material. By the time it reaches the sun's surface, the original gamma ray has been transformed into thousands of lower energy photons, mostly visible light and infrared radiation. The fierce, invisible energy of the core has become the warm, golden light that fills your sky. And then, the moment the photon breaks free of the surface, it races across the void at the speed of light and reaches Earth in just over 8 minutes. A journey of 100,000 years inside the sun, followed by an 8-minute sprint through emptiness. The light on your face carries a patience you can barely imagine. Spinning remnants of dead stars sweep beams of light across the cosmos. When certain massive stars reach the end of their lives, they do not simply fade away. They collapse violently, and what remains is one of the densest objects in the universe, a neutron star. These remnants are typically only about 20 kilometers in diameter, yet they contain more mass than the sun. A single teaspoon of their material would weigh billions of tons. Many neutron stars rotate at extraordinary speeds, a consequence of the conservation of angular momentum during the collapse. A star that once rotated slowly swells into a giant, collapses, and spins up like an ice skater pulling in her arms. Some neutron stars rotate hundreds of times per second. If the neutron star has a strong magnetic field, which many do, it channels radiation into tight beams from its magnetic poles. As the star spins, these beams sweep through space like the beams of a lighthouse. If Earth happens to lie in the path of one of these beams, we detect a regular pulse of radiation. These objects are called pulsars. The regularity of pulsar signals is astonishing. Some pulsars keep time more precisely than the best atomic clocks on Earth. They are natural timekeepers, embedded in the fabric of the galaxy, spinning and flashing with a reliability that spans millions of years. In the silence of deep space, they mark time with light, impatient and tireless, long after the stars that created them have ceased to exist. The most energetic light in the universe lasts only moments. Somewhere in the distant universe, right now, a star is dying. Not quietly, not gently, but in a cataclysm so powerful that for a few brief seconds, it outshines everything else in the observable cosmos. This is a gamma-ray burst, the most energetic flash of light the universe can produce. In a typical long gamma ray burst, the core of a massive star collapses into a black hole. As it does, jets of material are launched outward at nearly the speed of light, punching through the outer layers of the dying star and streaming into space. The energy released in those few seconds can exceed what the sun will produce over its entire 10 billion year lifetime. Short gamma ray bursts, lasting less than 2 seconds, are thought to result from the collision of two neutron stars, merging after spiraling toward each other over millions of years. The collision itself lasts moments, but the light it produces is staggering. These bursts are so bright that they can be detected from billions of light years away, and yet they are over almost as soon as they begin. A flash, a fading afterglow, and then silence. The universe's most powerful expressions of light are also among its most fleeting. There is a strange beauty in that. The brightest light the cosmos can create does not linger. It does not build gradually. It arrives in an instant, burns with incomprehensible intensity, and then fades into the same quiet darkness from which it came. Infrared light is the warmth you feel but cannot see. Just beyond the red end of the visible spectrum lies a kind of light your eyes cannot detect, but your skin can feel. Infrared radiation, with wavelengths longer than visible red light, is emitted by anything with a temperature above absolute zero. Your body radiates infrared light right now. The walls of your room radiate it. The Earth itself glows in infrared, a steady, invisible warmth pouring into the sky. When you hold your hands near a campfire and feel warmth without touching the flame, what you are feeling is infrared radiation. It travels at the speed of light, crosses the gap between the fire and your skin, and is absorbed by water molecules in your tissue, which vibrate faster and create the sensation of heat. Some animals have evolved to see in infrared. Pit vipers, like rattlesnakes, can have specialized organs between their eyes and nostrils that detect infrared radiation from warm-blooded prey. They can effectively see body heat in complete darkness, building a thermal image of the world around them. Infrared astronomy has revealed hidden features of the universe. Dust clouds that block visible light are transparent to infrared, allowing astronomers to peer into star-forming regions, the centers of galaxies, and the atmospheres of distant planets. Some of the most stunning images from the James Webb Space Telescope are taken in infrared, revealing structures that are completely invisible to the human eye. Warmth is light. It always has been. You cannot see it, but you have been surrounded by it, wrapped in it all your life. Ultraviolet light paints a world you have never seen. Just beyond violet, and at the high-energy end of the visible spectrum, lies ultraviolet light. Your eyes cannot detect it, but it is there, pouring down from the sun, reflected off surfaces, and interacting with the world in ways that would astonish you if you could see them. Many flowers, which appear as simple blocks of color to the human eye, are covered in intricate ultraviolet patterns. These patterns act as landing guides for pollinators. Bees, which can see ultraviolet light, perceive the flower as a target, with lines and markings that point directly toward the nectar. To a bee, a plain yellow sunflower becomes a vivid bullseye of contrasting UV patterns. Some birds also see in ultraviolet. The plumage of certain species, which appears dull to human eyes, blazes with ultraviolet markings visible only to other birds. What we perceive as a plain brown sparrow may, to another sparrow, be decorated with brilliant UV stripes and spots that play a role in mate selection. Human skin interacts with UV light in complex ways. Moderate exposure triggers vitamin D synthesis, essential for health, but overexposure damages DNA in skin cells, leading to sunburn and increasing the risk of skin cancer. The atmosphere's ozone layer absorbs the most energetic UV radiation from the sun, acting as a shield that makes terrestrial life possible. There's an entire visual world that exists just beyond the edge of your perception. Flowers are more decorated than you know. Birds are more colorful than you can see. And the sun paints the world in hues that no human eye has ever perceived directly. A hidden gallery of light, open to other species but closed to you. Our X-rays see through what visible light cannot. In 1895, a German physicist named Wilhelm Röntgen was experimenting with cathode rays when he noticed something strange. A fluorescent screen on the other side of his laboratory was glowing, even though it was shielded from the cathode rays. Some unknown form of radiation was passing through solid objects and reaching the screen. He called them X-rays, using X for the unknown. Within weeks of his discovery, Röntgen produced the first X-ray image, a photograph of his wife Anna Bertha's hand. The bones of her fingers in her wedding ring were clearly visible, silhouetted against the softer tissue that the X-rays passed through. When she saw the image, she reportedly said, "I have seen my death." The photograph became one of the most famous images in the history of science. Higher X-rays are a form of electromagnetic radiation, just like visible light, but with much shorter wavelengths and much higher energy. They can penetrate soft tissue but are absorbed by denser materials like bone and metal, which is why they are so useful in medical imaging. They are also emitted by some of the most energetic objects in the universe, including the superheated gas spiraling into black holes and the remnants of supernova explosions. It is a humbling reminder that visible light, the light your eyes are built to see, interacts with the world in only one narrow way. X-rays pass through walls. Radio waves pass through buildings. Gamma rays pass through nearly everything. The world you see is built from only one thin layer of reality, and beneath it, above it, and through it, other forms of light are moving constantly, unseen and unfelt. Radio waves carry human voices across the void. Radio waves are light. They are electromagnetic radiation, identical in nature to visible light, differing only in wavelength. While visible light has wavelengths measured in hundreds of nanometers, radio waves stretch from millimeters to kilometers. They travel at the speed of light. They reflect off certain surfaces and pass through others. And they have been carrying human information across space for over a century. The first intentional radio transmission is generally attributed to Guglielmo Marconi, who in 1901 sent a signal across the Atlantic Ocean. Since then, radio waves have become the backbone of human communication, carrying music, news, conversations, and data across continents and into space. And those signals do not stop at the edge of the atmosphere. They continue outward at the speed of light into the void. The earliest radio broadcasts transmitted in the early 20th century have now traveled more than 100 light-years from Earth. They have passed hundreds of star systems. If there are any receivers tuned to the right frequency within that expanding sphere of radio light, they could, in theory, hear echoes of early human broadcasting. Radio astronomy, pioneered in the 1930s and 1940s, turned this relationship around. Instead of sending radio waves out, scientists began listening to the radio waves arriving from space. They discovered pulsars, mapped the structure of the Milky Way, detected the cosmic microwave background, and listened for signals from other civilizations. The universe, it turned out, had been broadcasting all along, and we just needed to learn how to listen. Microwaves heat your food and carry the memory of creation. Microwave radiation occupies a curious place in the electromagnetic spectrum between infrared and radio waves. Its wavelengths range from about 1 millimeter to 30 centimeters, and it serves two roles in human life that could hardly be more different. In your kitchen, a microwave oven uses radiation at a wavelength of about 12 centimeters to heat food. At this wavelength, the radiation is absorbed efficiently by water molecules, causing them to vibrate faster, which generates heat. The food warms from within, not from the outside in like a conventional oven, which is why microwave food sometimes heats unevenly. But the same type of radiation fills the entire universe. The cosmic microwave background, with the afterglow of the Big Bang, peaks at a wavelength of about 2 millimeters and has been stretched by the expansion of the universe to microwave frequencies. Every point in the sky emits this faint radiation, carrying information about the conditions of the universe when it was only 380,000 years old. The cosmic microwave background was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Laboratories in New Jersey. They detected a persistent background noise in their antenna that they could not eliminate. After ruling out every possible terrestrial source, including pigeon droppings nesting inside the antenna, they realized they were detecting the ancient light of the universe itself. The same type of light that warms your coffee carries the oldest information in existence. Microwaves are both mundane and cosmic, both practical and profound. They are a reminder that the electromagnetic spectrum does not belong to any one purpose. It belongs to everything. Gamma rays are the most powerful light the universe creates. At the extreme high-energy end of the electromagnetic spectrum lie gamma rays. Their wavelengths are shorter than the diameter of an atom. Their photons carry more energy than any other form of light. They are born in the most violent environments the universe has to offer, in nuclear explosions, in the hearts of supernovae, in the accretion disks around black holes, and in the fleeting collisions of matter and antimatter. On Earth, gamma rays are produced by the decay of radioactive elements and by certain medical and industrial processes. In medicine, gamma radiation is used in cancer treatment, where precisely targeted beams can destroy tumors while minimizing damage to surrounding tissue. In imaging, gamma cameras detect radiation from tracers injected into the body, revealing the function of organs and tissues. In space, gamma-ray observatories have revealed a universe far more dynamic than visible light alone could show. The Fermi Gamma-Ray Space Telescope, launched in 2008, has detected thousands of gamma-ray sources, from pulsars to blazars to mysterious, unidentified objects. The gamma-ray sky is a map of the most energetic processes in the cosmos, a record of explosions, collisions, and annihilations that occur in scales and energies that dwarf anything in everyday experience. And yet you are shielded from nearly all of it. Earth's atmosphere absorbs gamma radiation before it reaches the ground. Without that shield, the surface of the planet would be bathed in radiation lethal to most forms of life. The atmosphere is, among its many roles, a gamma-ray umbrella, quietly protecting everything beneath it from the most dangerous light in the universe. Every photograph is a fossil of light. When you take a photograph, you are not capturing an object. You are capturing light. Specifically, you are recording the photons that bounced off a surface, traveled through a lens, and struck a sensor or a piece of film at one particular instant. The image is not the thing itself. It is the light the thing reflected, frozen in time. In this sense, every photograph is a fossil, not of bone or shell, but of light. It preserves a pattern of photons that existed for only a fraction of a second, a pattern that will never occur again in exactly the same way. The angle of the sun, the position of the clouds, the expression on a face, these all depend on conditions that are always changing. The photograph catches one unrepeatable arrangement and holds it still. The earliest photographs required exposures of several minutes. The subject had to remain perfectly still while enough photons accumulated on the plate to form an image. In those early days, a photograph was not an instant, but a slow gathering, a patient collection of light over time. Today, cameras can capture images in a thousandth of a second or less, but the principle has not changed. Light arrives, it is recorded, and the resulting image becomes a permanent trace of a moment that has already passed. Every family album, every news photograph, every image from a space telescope is a collection of fossilized light, a record of photons that once existed and were caught just before they vanished forever. Shadows are proof that light exists. A shadow is not a thing. It is an absence, a region where light has been blocked. And yet, shadows have a presence of their own. They have shape. They have edges. They move when the light source moves. They stretch in the morning, shrink at noon, and lengthen again in the evening. They are as much a part of the visual world as the objects that cast them. But here's the quiet truth about shadows. They can only exist where light exists. Darkness alone cannot produce a shadow. A shadow requires a light source, an object to block it, and a surface to receive the absence. Without light, there is no shadow, only uniform darkness, featureless and flat. In this way, a shadow is not the opposite of light. It is a creation of light. It is the shape that light draws around the things it cannot reach. Every shadow you have ever seen is evidence that somewhere, from some direction, light is shining. Artists have understood this for centuries. In painting, shadow is not the absence of detail, but a tool for creating depth, drama, and emotion. The interplay of light and shadow, called chiaroscuro, is one of the most powerful techniques in visual art. It is the contrast between the two that gives an image dimension, that makes a flat canvas feel like a window into a three-dimensional world. Tonight, if there is any light in your room, there are shadows. They drape over the folds of your blanket. They pool in the corners. They soften the edges of everything around you. And each one, quietly, is a tribute to the light that made it. Starlight is the oldest story anyone can read. When an astronomer points a telescope at a distant star and spreads its light into a spectrum, something extraordinary is revealed. Dark lines appear at specific wavelengths, thin gaps in the rainbow of color. These are absorption lines created when elements in the star's outer atmosphere absorb particular wavelengths of light passing through them. Each element produces a unique pattern of lines, as distinctive as a fingerprint. Hydrogen absorbs at one set of wavelengths, helium at another. Iron, calcium, sodium, oxygen, each leaves its own signature. And by reading these lines, astronomers can determine what a star is made of, without ever touching it, without ever visiting it, from a distance of billions of light years. But the spectrum reveals more than composition. The width of the lines indicates temperature and pressure. The shift of the lines tells the star's velocity, whether it is moving toward us or away. The overall shape of the spectrum reveals the star's surface temperature and luminosity. From a single beam of starlight, an astronomer can construct a detailed portrait of a star, its mass, its age, its chemical history, its place in the life cycle of stellar evolution. Light is not just illumination. It is information. It is a language written in wavelengths, spoken across the void, and understood by anyone who knows how to read it. The stars have been broadcasting their stories since they first ignited, and they will continue long after the last human eye has closed. Light is the universe's memory, and it forgets nothing. Darkness is not the enemy of light, it is its canvas. We tend to think of darkness as the absence of something, as a void, a lack, a negation. But darkness is not opposed to light. It is the space in which light becomes visible. Without darkness, light would have no contrast, no shape, no meaning. A universe of pure light would be as featureless as a universe of pure darkness. Stars are only visible because the space between them is dark. A candle flame only draws the eye because the room around it is dim. The beam of a flashlight only has direction because the air surrounding it is unlit. Light needs darkness the way a voice needs silence, not as an enemy, but as a frame. In your own experience, darkness has a purpose too. It is the condition under which your body rests. It is the signal your brain needs to begin the transition towards sleep. Melatonin rises in darkness, muscles relax, thoughts slow. The absence of light is not emptiness. It is invitation, a gentle opening toward rest. Tonight, the darkness around you is not something to resist. It is something to settle into. It is the canvas on which the last images of your day are fading, making room for the soft, formless quiet of sleep. Light will return. It always does. But for now, the darkness is doing exactly what it should, holding space, asking nothing, and offering you the gift of rest. You are made of light in a way. Every calorie of energy in your body can be traced back to light. The food you eat, and whether it is a grain of rice, a leaf of lettuce, or a piece of bread, began as sunlight. A photon left the sun, crossed 150 million kilometers, struck a chlorophyll molecule in a leaf, and set off a chain of chemical reactions that stored that energy in the bonds of sugar molecules. You ate the plant, or you ate something that ate the plant, and that energy became yours. The ATP molecules powering your cells right now carry energy that was once a photon. The electrical signals traveling through your neurons are sustained by metabolic processes fueled, ultimately, by light. The warmth of your body, the beat of your heart, the thoughts forming quietly in your mind as you listen to these words, all of it is running on energy that was once sunlight. And it goes deeper. The atoms in your body, the carbon, oxygen, nitrogen, and iron were forged in the cores of ancient stars, in nuclear reactions that produce both heavy elements and light. Those stars exploded, scattering their contents across space, and from that debris, new stars, new planets, and eventually you were assembled. You are not just illuminated by light. You are built from processes that created light. You are sustained by energy that was once light. And when you look up at the stars, the light entering your eyes is made of the same fundamental substance as the light that once built the atoms you're made of. You are light rearranged, and that is not a metaphor, it is physics. And now let the story of light gently fade into quiet wonder. We have followed light across an extraordinary distance tonight. We began behind your own eyes. In the tiny delay between a photon arriving and your brain assembling a picture of the world, we watched light split into colors through rain and glass. We discovered that the green of every forest is the color that life turns away, and that the darkness of the night sky is not emptiness, but evidence of a universe with a beginning. We traced the path of a single photon from the core of the sun, where it struggled for 100,000 years through dense plasma, to the surface, where it broke free and crossed the void to Earth in just 8 minutes. We followed humanity's long relationship with light, from the first controlled fire over 1 million years ago, through the flickering patience of candles, the golden glow of gas lamps, and the electric blaze that dissolved the ancient boundary between day and night. We listened to the whisper of Voyager's radio signal, 22 hours away and fading. We saw light bend around galaxies, revealing hidden worlds. We met the creatures that carry their own lanterns through the dark, from fireflies writing love letters in meadows to deep-sea fish glowing in waters that have never seen the sun. And we learned that even your own body emits a faint, invisible glow, a quiet luminescence too faint for any eye to see, but real and constant and yours. Through it all, a single truth kept returning, soft and steady as the light itself. You are not separate from light. You never have been. The energy in your muscles, the warmth of your skin, the electrical storm of thought behind your eyes, all of it began as a photon somewhere, sometime, in a star that may no longer exist. You are light that has learned to wonder about itself. Tonight as you rest, light continues its work. Somewhere a photon is leaving a distant star, beginning a journey that may last millions of years. Somewhere bioluminescent plankton are lighting up a dark shore. Somewhere, the cosmic microwave background, the oldest light in existence, is passing quietly through a sleeping world, carrying the memory of the universe's first transparent moment. And here, In this gentle darkness, you are lying still. Your breathing has slowed. Your thoughts are softening at the edges. The light behind your eyelids is fading, not because it is gone, but because your body is doing what it was made to do. Resting, recovering, preparing for tomorrow when the first thing you will see, before anything else, is light. It will be there. It always is. So let your eyes stay closed. Let the last images of the day dissolve. Let the darkness hold you the way it has held every living thing since the first night fell on the first world that ever turned away from its star. Sleep well, and when you wake, the light will be waiting for you, patient and unchanged, as it has waited for 13.8 billion years. Good night.